What is photoelectric effect? The photoelectric effect, Hertz in 1887 discovered that when ultraviolet light falls on certain metals, electrons are emitted. This phenomena, in which certain metals emit electrons when exposed to high frequency light, is called photoelectric effect. The experimental arrangement to demonstrate the effect is shown in figure 17.9. The observed photoelectric effect has these features: increasing the intensity of the source of light, increase the number of photoelectrons, but not the velocity with which they leave the surface of the metals. For each substance, there is a certain frequency called the threshold frequency, below which the effect does not occur. The higher the frequency of the incident light, the greater the kinetic energy, 1 over 2 mv square of the photoelectrons. Attempts were made to explain these aspects of the photoelectric effect from the point of view of classical wave theory of light, but no successful explanation was obtained due to the following reasons. From classical theory, there should be no threshold frequency, because at a given time, electrons might absorb enough energy from the incident light to escape from the metal surface at any applied frequency. The the velocity of photoelectrons should depend upon the amplitude of the wave incident on the metal, and therefore upon the intensity rather than the frequency. Let us first discuss the experimental results of the photoelectric effect. If we draw the photoelectric curves by plotting the photoelectric current I versus the accelerated voltage V, we will obtain the curves shown. These are the curves shown. From these curves, it follows there is a saturation current from different intensities I, 1, 2, 3, etc. And even when the potential V is equal to 0, there is some photocurrent IO and a negative potential minus V naught called stopping potential. This behavior of photoelectric curves indicate that the stopping potential is independent of the intensity of the source, and the kinetic energy K of the photoelectrons will be maximum for the condition. K maximum is equal to 1 over 2 m. This maximum is equal to C, where V maximum is the maximum velocity of the photoelectrons, E is equal to charge of electron. If photoelectric curves are plotted for different frequencies V1 and V2 but the same intensity 1 I of the following of the source, the curves show up the following behavior figure. This from these curves we infer that the saturation current depends upon the intensity and not the frequency. However, the stopping potential becomes more negative from V01 to V02 with an increase in the frequency V2 greater than the V1. The variation of the maximum energy of the photoelectrons, K maximum, as a function of frequency may be seen from figure 17.12. The graph shows a threshold frequency V naught is the minimum frequency below which no electrons escape the metal surface. The most significant feature of this graph is that the slope of the line gives the ratio h over e. Thus, if E is known as the measured slope, provides a value of Planck's constant h quick independently.